All right, great.
Yeah,
so let
everything
us,
is-
perfect. Let us continue. So we are going to go to a new chapter. So it is, this one is, we are going to discuss small quantum cohomology. This is what we are going to spend several sessions on, quantum cohomology. So now that we have a good understanding of Gromov-Witten classes and Gromov-Witten invariants, we would like to define this modification of usual cohomology theory of a given variety in terms of Gromov-Witten invariants. So recall the following. Given T0 equal to 1 and T1, T2, all the way to T of M, elements in the cohomology theory of X with rational coefficients. If I look at it as a tuple, it would be an element of tensor product of X with itself, cohomology of X with itself, M times a basis. So we have some variety with the basis of its cohomology theory. Let us define this thing. We had this before. Gij is the intersection form on this variety. It is actually cup product intersection of cycles Ti and Tj. And we also had a definition that G upper index Ij, I mean, this intersection form has a vector matrix representation, and this matrix is invertible, and this upper thing is the inverse of the intersection matrix itself. So it is G to the minus 1. Okay, so this is something that we actually used in the splitting axiom. We had as coefficients elements of Gij appearing. If you remember, when we were breaking the curve, we wanted to identify the points, the 2 points on the 2 parts of the curves with each other. We were replacing those empty spots with Ti and Tj, and this intersection entries were appearing. Okay, so now let us we need this extra thing. So let omega be an element of H2X. You see, the intersection, these are bases of cohomology theory of X with rational coefficients. Omega is an element of H2 of X with complex coefficients. So I'm going to have let this be complexified kahler class. So it's the class of the kahler form, okay? It's the class of the kahler form on that variety, the canonical form, kahler form on that variety, okay? All right, so it's a codimension one, I mean, it's like a line bundle, and the divisor, theoretically, it's a divisor for codimension one, complex dimension, and so it's sitting in H2. Okay, so let's say that this is complexified kahler class, then definition. Definition is let omega be complexified kahler class on a smooth projective variety X. Okay, so we would like X to be smooth and projective. Then for I'm gonna call them A and B, two elements of rational cohomology of X. Okay, for two cohomology classes in X, we define a product. Define a certain product of A and B. So what is this product? It is A, I'm gonna call it A star B, and it's going to be summing over I and J and summing over O beta in second integral homology. You see, betas are going to be curve classes. So I would like really integer coefficients. I don't want to think about 3/5 of a curve or something. I don't want that, right? So Okay, so these are curve classes, and then there is going to be a sum defined as follows. So I0, 3 beta, A and B. When I put 0 in here, it means I have 3 mark points, right? So I'm looking at curves with 3 mark points on it, and I need to pin these points to 3 cycles in my ambient variety. Two of these cycles are going to be A and B themselves, you see? Okay? And then the third is going to be the TI. Oops. So I don't like to be not clean. So write it like that. And then this is the Gromov-Witten invariant. So it comes as a coefficient in this. And then it further continues times Gij, okay, times something that keeps track of which curve class I am picking. So Q to the beta, all right? And then times Tj for all I and j, where Q to the beta is defined as e to the 2 pi I. It should be a number, right? So Q to the beta doesn't have any meaning, but now it will have a meaning. Look, so it is the complexified kahler class of X, yes, integrated against beta. So this guy, kahler class, is sitting in H upper 2, beta is sitting in H lower 2. That's a number. E to the 2 pi I times number is a number. Yeah, good, fantastic. So this gives us a number times this guy, which is the basis of the cohomology. So this is actually very similar to usual intersection theory of cycles. When you have 2 cycles associated to a variety, the intersection product of those 2 things is the number of intersections, right? If you have, for instance, 2 curves, right? 2 curves like that, this thing is sitting in H lower 2 or H whatever, n minus 1, right? 2n minus 2. And this thing is sitting in H 2n minus 2. So, okay, we know that their intersection is going to be well defined and let's say transverse. So if you actually take the intersection product of these 2 things, this has a cohomology class A and this has a cohomology class B. And A cap B is a number, is the number of their intersections, so number of intersection times what? Times some cohomology class, right? So that's times point class. So it's always intersection theory produces you a class in the ambient cohomology theory of the variety. Similar thing in here. So we are producing a class out of this weak intersection product. But as we discussed, this is not exactly intersecting the varieties. This is basically saying I have 2 cycles and I'm, constructing some kind of a weak notion of intersection between them, meaning kind of looking at their weak intersection as a system of curves having intersection with each one of the cycles, right? So this is called, which is called small quantum product of A and B. Okay, this is what that is. So what does it look like? So okay, so this is X, right? I have a cycle A and I have a cycle B. And then I'm looking at curves passing through these 2 like that. I count how many curves are passing through these 2 whose third point, so these are genus 0 curves. They have 3 mark points, and the third point, the P3, so P1 is on A and P2 is on B, and the P3 now depends on the cycles that I choose, Ti. Okay, so I will just start from Ti equal to 1, which is the fundamental class of ambient X. Then Ti equal to next one, T1, T0 equal to 1, then T1, then T2, and it keeps going. So I'm gonna choose based on these things whatever. So let's say all the curves that these have intersection with, all the surfaces that these have intersection with, all the way up to codimension 0, the whole variety. So this actually tells me how many such curves are there. And that's this number, right? And then the rest is Gij q to the beta Tj is the remaining coefficient of the cohomology class for that Tj. So in some sense, it gives you a combination of Tj's coupled with coefficients, which actually tells us how many curves have these intersection this way, this particular way, with A and B and Tj. Okay. This curve is genus 0, so it's actually a P1, right? It's a map from P1 into the ambient variety. Okay. Here's the remark. The issue, any questions, by the way, so far? Okay. The issue with this definition, is that the sum over this curve class beta, right, might be infinite. Might be infinite. It's true. I can pick elements of integral homology, infinitely many elements like that. Infinitely many curves with curve classes beta that have intersection with A, B, and Tj's, right? So we might need to modify somehow, modify q to the beta. We want to modify q to the beta so that this sum does not become infinite. Okay, so let's just see how to do that. So let us define Ti's equal to summing over j's Gij Tj. So this T0, T1, all the way to T of M, dimension of the ambient variety, form a dual basis of T0, T1, T lower M, right? Satisfying the following identity. So if I have intersection of them should be chronic or delta, right? So if I have, so better to put, well, it doesn't matter, but anyways, better to put this like this, Tj, I would like to get the chronic or delta. That is the dual basis. All right. So let's say this is the dual basis, then we can write the small quantum product the following way. So the small quantum product as, so look at the small quantum product, right? So give me a second, guys. All right. Any questions, by the way? Can you actually confirm that you can hear me?
Yes, we can hear.
Yes,
Okay.
I hear you.
Perfect. Sorry, I just received the message and I am going to, just give me a second. There's some kind of a glitch in here. I need to attend this thing. Just give me a second, please. Okay, sorry about that. Yeah, no problem. Okay, yeah, so sorry. So look at the sum here, you see, I already have it, right? So Gij times Tj is the T upper index I, right? So this is how we are defining this thing. Gij Tj summing is T upper index I. So then we can write the small quantum product the following way. A quantum product with B is going to be summing over all I, beta, H2 integral homology I0 3 beta A, B, and T, I, yeah, Q to the beta, and then Ti. Of course, that now I have gotten rid of this double sum with respect to J. Now, second remark, I'm going to prove that this thing is going to be giving you a finite thing. So, remark, previously, I, G, and beta inside the brackets were defined for rational cohomology classes, rational cohomology elements. Right? However, we have here extended the definition by linearity to complex coefficients. So definition to complex coefficients by linearity, so that I0 3 beta A, B, and Ti, this number makes sense even for cohomology classes with complex coefficients. So makes sense for A and B in H upper star of X with complex coefficients. Yeah? So this is what it is. And then here is a remark. For beta in second integral homology of X, the degree axiom, I mean, essentially the finiteness of that sum is the combination of the properties of Gromov-Witten classes, basically. So for beta, the degree axiom implies that I0 3 beta of A, B, and Ti is going to be a zero number invariant unless the certain degree constraint is satisfied. You remember it. So degree of A plus degree of B plus degree of Ti's, right, is equal to 2 times dimension of X minus 2 times integral of the Kahler class of X against beta. Now, these are genus 0 ones, where omega X is the canonical class. Canonical class on X. Okay, here's a proposition. Let X be the smooth projective variety, such that either, number one, X is a Fano variety. Number two, X has transitive action by some semi-simple Lie group, by some semi-simple Lie group. Okay. Then, if that's the case, okay, I don't want to put that in here. Then the sum in A star B is finite for any A and B in a complexified cohomology of X. You see, that's why I made those remarks. So if we have extended this thing to complexified cohomology, we reminded ourselves of the degree axiom and the constraint it puts on the degree of the cohomology classes. Now here is the proposition. This sum can be finite in these two terms. Why? Very easy. So proof, we show that there exists finitely many ABs, okay, for which the degree condition is satisfied. Okay, and are represented by genus zero stable maps, represented by genus zero stable maps. Okay, so only finitely many ABs satisfy this condition, the degree axiom. Okay, so first of all, case one, if X is Fano, Fano variety, Fano variety means that, you know it means that the canonical bundle of X has negative degree. That's meaning minus canonical class of X. Divisor theoretically is bigger than zero, right? So you understand that this is in the kahler cone. So this inequality is in the kahler cone, right? So it really means that minus omega of X, yes, if I integrate it against curve classes, is going to be always bigger than zero for all betas. That's what it means. Effective. It's an effective, anti-effective divisor itself. Effective divisor means you have curves and you're passing through the surface defined by the divisor associated to the omega of X. It's a line bundle, so it's a divisor, curves pass through it, okay. They have a positive number of intersections. That means effective, numerically effective, right? So anti-effective means minus that thing is numerically defective. And this thing is actually exactly intersection of that divisor defined by the canonical bundle and the curves by anti-canonical bundle. So I'm thinking about everything divisor theoretically. So when I want to put a minus, the divisor will have minus next to it. Or I can think about the line bundle associated to omega of X, and I'm flipping the sign of its degree, right? So usual kind of algebraic geometry. So this inequality is in the kahler cone on the on the closure. It's defined on the closure of the cone defined by these curve classes, right? Of the cone, say, generated by betas, by these betas. So, okay, so if it is Fano, like projective space is Fano, right? Then that's the case. P2. P2, its canonical bundle of P2 is O of P2 minus 3. So because its degree is negative, minus this thing, the divisor is going to be OP2 of 3. And it will be a surface, hypersurface positive degree. And if you intersect it with betas, you will get positive numbers. Okay. So if X is Fano, then omega of X against beta will be less than a constant. So I'm going to put a constant, less than a constant for only finitely many betas. Okay. That's what it's going to be. Okay. All right. So that I think is kind of clear. So you can actually see that the rest of them, so this Q, I mean, the power of E, where is it? Q to the beta, right? Q to the beta is E to the 2 pi I. Where did I define it? Here it is. So this is what it is. If it is final, this quantity here, right? This quantity here starts from being maybe, I mean, constant, but at the more and more beta you put there, this intersection product is negative. So as you can see, this exponential function decays and approaches zero very quickly. And so basically only finitely many terms can survive this intersection. So for Fanos, it's kind of clear. Okay, so now, next, assume X has this action of a semi-simple Lie group, the transitive action of semi-simple Lie group. So it's going to be something like a Lie group here, divided by some parabolic subgroup. So this is a parabolic subgroup. Yeah. Then the cohomology of this variety X is known. And beta represented by genus zero stable maps, zero stable maps, okay, are non-negative. Non-negative integer combinations of finitely many beta 1 to beta r, such that each beta I is the image of a non-constant map. Let's call that map mu I from P1 into the ambient variety X. Okay, so what is it saying? If you have this kind of a variety, homogeneous variety given by the quotient of a Lie group by the parabolic subgroup of it, in which case you have this transitive action, free transitive action of G on it, yes, then we are trying to prove that this sum is not infinite. So first it says you have restrictions on the betas. Those betas which are represented by genus zero stable maps are not just wildly random. They are all non-negative integer combinations of only finitely many betas. Okay, and these are genus zero, all of them, and they are maps from P1 to X. So we are going to call beta I the map mu I from P1 to X. Then it suffices to show that similar to before, this identity is satisfied for these beta i's, or equivalently, or because I can, swap it, I can say first Chern class of the tangent bundle of the variety against beta I is bigger than zero. This is the canonical bundle, that's the tangent bundle. So one of them is, yeah, minus the other. Okay. So you C1 of it, C1 of it, that's the Kahler class. This is the Kahler class, and that's the C1 of the tangent bundle. So why am I writing in terms of the C1 of the tangent bundle rather? Because we know that T of X is globally generated. Remember that X is a convex variety. Its tangent bundle is globally generated, which implies that mu I upper star of T of X is also globally generated, over P1, right? The convex variety had this property that you have the map from P1 into ambient X, right? And you were looking at the tangent bundle in here, and you were basically arguing that if I pull back these mu I upper star of tangent bundle, this is going to be 0 for all I not bigger than 0. So the only thing that survived is the H0. It's a globally generated bundle on P1. Yes. So mu I upper star of Tx is a vector bundle, doesn't have any higher cohomologies, so its sections can be extended everywhere on P1. So it's going to be a vector bundle on P1. But there is something called Grothendieck lemma, which actually says if you have a vector bundle on P1, a locally free sheaf on P1, it basically splits as the sum of line bundles. It's a very, very important result. So this is the vector bundle of given rank on P1. And hence, by what is called Grothendieck lemma. Okay, you can find this. It's a sum of line bundles, meaning it's going to be written as sum over J, right, of line bundles on P1. But what is a line bundle on P1? It is O of P1 up to some twist. O of AJ for some AJ is bigger than 0. Okay. Now, if we prove, so it could be either trivial bundle, right, or positive numbers. So if we prove that AJ is actually strictly bigger than 0, then this shows that because of this quantity, I mean, if I integrate C1 of this whole thing, it has to be written in terms of AJs, because intersection, this thing that we are trying to calculate, now this C1 of the pullback of the tangent bundle is the C1 of the sum of the OP1 AIs, and that's basically the degree. So if we prove that all of them are bigger than 0, then that total sum is going to be bigger than 0. So this thing is going to be negative. Then by the same argument that we had before, this sum that we defined in here, this guy will decay very fast, and only finitely many terms in this double sum would survive. Okay, so is that the case? So if we prove that this is bigger than 0, then integral against beta j of C1 of tangent bundle of X is going to be bigger than 0. Okay, assume not. Assume that's not the case. Then, well, the only other possibility is that this thing is the trivial bundle. Trivial bundle. Then T, if I look at the tangent bundle of P1, it actually maps to pull back. This is the Euler sequence, pull back of the tangent bundle of Tx. Yeah, if I pull back cotangent bundle, it maps to cotangent bundle of P1, but in level of Euler sequence, basically tells you tangent bundle of P1 maps to pullback of the tangent bundle of X. And then this would be the zero map. Okay, I'm going to ask you, why is this going to be the zero map? Anyone? You know that this is a trivial bundle, and I'm saying that this map is going to be the zero map. Does anyone know?
Okay. Does this follow from the exactness of the Euler sequence?
Not exactly. There's a certain property that gives you that. You have vector bundles, and there are certain criteria about maps between the vector bundles. Here is one. Tangent bundle is a stable bundle. Stable bundle. Okay? And if you have two vector bundles, and both of them are stable, tangent bundle of P1 is stable, tangent bundle, pullback of the tangent bundle of Tx is stable, then the map will be zero if the degree of this bundle, if the degree here is bigger than the degree here. In order to, so basically it says that if you have a map between two stable bundles, if you look at the degree of these vector bundles and the degree drops by the map is going to be zero map. So why is this the case? Since the degree, so T of P1 is in fact exactly O of P1 twisted by 2. Omega of P1, which is the same thing as canonical bundle, oops, P1 is dimension 1, so it's the same as canonical bundle of P1, is OP1 minus 2. Tangent bundle is the inverse of that. So in terms of a bundle, is going to be OP1 2, positive 2. Now this degree is bigger than 0, but by our assumption, this is less than, equal to 0. It's a trivial bundle. You have a map between stable bundles A to B such that degree of A is bigger than degree of B has to be zero map. It's a statement, okay? Has to be zero map. Okay, so this map cannot be, so this has to be zero if the pullback is trivial bundle. Yes? Then, but this is impossible. However, this is impossible because since mu i's, if the map is zero map, then that means we have assumed, because it's impossible since in that case it implies that the map mu I from P1 into ambient X, right, is a constant map. Which is a contradiction with assumption, which is a contradiction. There are finitely many curves, beta 1, beta r, for a homogeneous variety G modulo parabolic subgroup P, such that all the curves are generated by these finitely many beta 1, beta r's, and the map that produces these curves with these classes are non-constant maps. If the pullback of the tangent bundle is trivial bundle, it means that these maps are constant for all of them. It's a contradiction. Okay. So basically that's that. Now I assume that maybe some of you, there are certain mysteries for you here. So maybe to help you understand it, I suggest you to go and look at stability of bundles, stable bundles, stability criteria. What's the stable bundle mean? What is the stability criteria for bundles and sheaves? Okay, for bundles, I can tell you. So given a bundle A, there exists a notion of a slope of A, which is slope of A is defined by degree of A modulo rank of A. You look at the degree of your bundle modulo its rank. For instance, if I have OP1 of 2, then the slope of this OP1 2 is 2 divided by 1 because it's rank 1, it's 2. If I have O of P1 plus O of P1 minus 3, then I call this thing whatever, V, then the slope of V is going to be its degree. Degrees of some of the bundles add up. So that is minus 3 divided by its rank, 2. So on and so forth. Now, in the realm of vector bundles, a bundle is called a stable if for all a bundle V or A is called the same if for all B sub-bundles of A, we have that slope of B less than slope of A must be. It's called semi-stable actually if slope of B is smaller than equal to slope of A. And it's called unstable if this inequality, otherwise unstable. Okay, so this is the notion of stability of vector bundles. It has to do with degree divided by rank. Now, this is going back. If this thing is a trivial bundle, the slope is equal to 0, but the slope of this one is actually equal to 2. You see, 2 divided by 1. If you have a map between two vector bundles such that both of them are stable, satisfying that condition, this means that any vector bundle B that you put in here is a sub-bundle of T of P1. It satisfies the inequality of stability. Any vector bundle B prime that you put in here, sub-bundle of pullback of this satisfies that inequality. Okay. If you have map between two stable bundles, but the slope drops, that map has to be 0. 0 map. Okay, so we have the notion of stability for sheaves as well. Okay. So that is not with this slope. Of course, we can define a slope for sheaves as well, but for sheaves, you need to use the Hilbert polynomial of the sheaf to define the notion of a slope. So somehow you will be looking at the degree, coefficients of Hilbert polynomial of that sheaf. But we will do that when we go to Donaldson-Thomas theory. If it comes up, because we are going to use with the stables, use the stable sheaves and so on, we will use that and review it. Okay, so that's the proof. Okay, so this is that statement. Now let us talk a little bit about properties. So there are finitely many betas for this. This is going to be defined as quantum product. So properties of a small quantum cohomology. Okay, So here is a theorem. There's a theorem. H upper star of X with complex coefficients is a supercommutative ring with identity under the small quantum product. Quantum product. What does this mean? That is to say the following. If I take a quantum product B, two elements of extended complexified cohomology theory of X, is going to be -1 to the degree of A times degree of B, B star product A. So if I think of cohomology ring as a ring, because it is a ring, yes, then these are parameters or variables in the ring. A times B is minus B times A, or the way it's actually written, -1 to the degree of A times degree of B, it gets modified by that sign, B cross A, B star A. Okay? So, all right, so how do we see this? This follows by, follows by a covariance axiom. That is the following. So let us remind ourselves what was the equivariance axiom. So here is the equivariance axiom for Gromov-Witten classes and Gromov-Witten numbers. So if I take I0, 3 beta, I need to have 3 markings, so 3 cycles, A, B, T, I, then calculate that invariant. It's going to be -1 to the power degree of A times degree of B times Gromov-Witten invariant I03 beta BATI. As soon as I shuffle these, remember that the cyclic group, the symmetric group, is acting on markings. I can swap the place of P1 and P2. Yes. And then, okay, my Gromov-Witten invariant just gets modified by a sign. Yeah. So this is something that we have. Moreover, we had something else. Moreover, let T0 equal to 1. So what does this mean? Constant. It means that it's codimension 0, right? So it is the fundamental class of the whole variety X. So this lives inside this thing. Everything now we have extended into complexified cohomology theory. Fundamental class. Fundamental class. Yes. Then, so first part is actually a result of equivariance axiom. So it's a supercommutative ring, we are saying, with identity under the small quantum product. The fact that it's a supercommutative ring is because of the property of Gromov-Witten invariance and the Gromov-Witten classes. That's one thing. But right now we are focusing on here. Why does it have identity? What is the identity of this ring? Statement is that identity of this ring is going to be the fundamental cycle. So I want to have some notion that this basically gives me A or something. Okay, but let's see. So, all right, let's see. So we know that I03 beta A T0 T I, remember that T0 is fundamental cycle of X, is equal to 0 whenever eta is not equal to 0. So this is the fundamental cycle axiom, right? Cycle axiom. Okay, but then that's great, because then as soon as I take A times T0, I will get a sum. Let me just expand that formula that we had. I will get a sum I0, 3. Well, it's going to be 0 invariant unless this is the 0 class, right? So it's going to be the constant map only surviving. So this is going to be like that. And then A T0 Ti, yeah, times Ti, basically. And that's going to be summing over all I. Well, it's the constant map. The map is taking one more time. I would like you guys to always have this visual point of view, what's happening. It's a constant map. It takes a P1, yes, P1 into this ambient variety. This P1 has 3 points on it. And these 3 points are gonna land on class A, cycle A, and cycle T0 and Ti. But the curve class has to be 0 for this invariant not to vanish. So this map is a constant map. It takes all of this into a point. This picture is being mapped to a point. Where should that point be? That's clearly intersection of the 3 things, A, class A, and the T0 and Ti, right? That's basically it. So it's going to be integral over x of A cup with T0 cup with Ti. That's the only possibility, because it's going to map it to a point. Better be on intersection of the 3. All right. So everything is being mapped on a point. So T0 and Ti and A are going to have to have intersections with each other. And we are calculating that number times Ti. So this is the point mapping axiom. You see, all of the things that we did before are now helping us to define this notion of quantum product. But okay, but then what is that? That is equal to A intersected with T0, in fact, which is just A. Yeah, and because look at this. Yeah, okay, so that's it. We can see that this is a supercommutative ring, and if I take the class A and multiply by T0, which is the same, so otherwise also A intersected with fundamental class of X is just A. So this ring is a supercommutative ring with an identity, and an identity under the small quantum product is the fundamental cycle of X. Okay. So, okay, hence we get identity for the star product. Now we prove that, okay, so we have the supercommutativity, we have the identity property. There is something else that we need to show. We prove that this star product is an associative product, so it is associated. There's a ring, right? Okay, let's just see. We use splitting axiom this time. Splitting axiom. So how do we do that? Let A and B and C be element of the complexified cohomology of X. Yes. These homogeneous elements, are given. So I would like to show this thing. Consider, we would like to show associativity. So we want to show, so claim is to show that something like this is okay. So I want to do this thing, and then I show that this is the same as this thing, right? That's associativity. Okay, so let us define it. So consider the first one. So A, the star product B, then the star product C. What is that? So first, I'm going to define A star product of B, right? So, okay, so this is kind of a little bit convoluted. So I'm summing over all curve classes, summing over all T and U, yes, of summing over all beta 1 plus beta 2, yes, summing again over all R and S, G RS times I03 beta 1, A and B and TR times I03 beta 2 of TS and C and T of T or something, T of T. Okay, so actually, let me put this in a better position because I don't like it. This is not being seen very well. So times I03 beta 1, right? Okay, all the curve classes. So I'm gonna add, so I'm gonna look at A and B first, quantum product. So these curves are going to have to be having class beta 1. They have incidence with A and B, and then some additional cycle, which is going to be for me TR. So first I do that. So A and B and then TR. So okay, that's the coefficient. And then this is modified by some cohomology class, T. So there is some T that comes in here. And now that is class of A star B. And I'm taking that and I'm multiplying it again by C. So what do I get? I get the second coefficient, I03 beta 2 of TS, C, and T, whatever, T maybe, T, like that, times G to the TU times Q to the beta times T. Right? So let's see, are we making sense? Yes, so we are adding over T and U, we are adding over betas. Betas are going to be beta 1 plus beta 2. We are adding over T and U, this is okay. We are adding over beta, that's okay. And then we are left still with some extra class TU, that makes sense. Yeah. And these two things are being absorbed into the sum.
Can you explain here these two sums over beta? What do they mean?
It means that I'm looking at the condition. I'm looking at all curve classes beta 1 and beta 2 so that it becomes equal to beta.
Okay, so so the second sum in brackets is the sum over beta 1 and beta 2 satisfying this condition. Satisfying
that condition, exactly.
Okay,
exactly. That's right. So it's the, yeah. So good questions. This such that beta 1 plus beta 2 is equal to beta. Exactly. Okay, so if you open it up, this is exactly what you will get. All right, so that's that. Now consider, so how do we even do this thing here? Now consider I0 4. I'm gonna bring in I04 beta. Why? Because look at it. I have product of I03 and I03. I03 and I03. Okay. Beta 1 and beta 2. And I'm looking at curves, you know, that basically have curve classes beta 1, beta 2, and then I'm adding all of the possible curve classes beta 1, beta 2, such that beta 1 plus beta 2 is equal to beta. So it seems to me that, to us, that there is a curve with class beta, and we are splitting it. Okay, so let us actually see how can we cook that up as a map. So it's an I0, consider this I0 A, B, C, and T of T. Okay, you will say, why do I need that? The splitting axiom gives the following map. Gives, you remember, phi m bar 03 times m bar 03 goes to m bar 04, which is itself a P1. You remember this one, right? So if I take a curve with 4 mark points on it, then splitting axiom tells me I can divide them like that. And then I have to have these, but then you see, you have this extra point in here. So each one of those pieces will have 3 mark points on it. So this one has I03 and this one has I03 associated to it. And you know, splitting axiom relates the tensor product of these two things, or the product of the invariants associated to this thing, to something coming from M04. And that's basically right here. Okay, so then under this map phi, I'm going to put it again like that. Yes. Upper, what is it? Phi upper star of I04 beta is not equal to 0 unless, then under this map, let's put it this way. Under this map, we can describe the pullback. The pullback phi upper star of I04 beta, that Gromov-Witten class, which is going to be not equal to 0 unless I04 beta A, B, C, and T of T is going to be an element of H0 of number 04. Yeah, we had that, unless its codimension is 0 in the degree, it sits in the degree 0 part of cohomology, this is going to be a non-zero map. So now let's just see. Remember that this is a point, and this is also a point. M03 is genus 0 curves with 3 markings on it. These are P1s, right? And they are identified with the 3 canonical points of P1. So basically, this is just a point mapping to a P1. So since the map phi is the inclusion of a point of P1, yes, then we can regard the pullback I04 beta A, B, C, T of T as a number. as a number, which by splitting axiom is going to be, isn't that interesting? Yes. Pullback of a class is going to be the tensor product of the Gromov-Witten classes. Yes. But then, because the domain of the map is just 0, its cohomology theory only has degree 0 part, and that's going to be numbers, right? So it's a constant. So pullback of that Gromov-Witten class is going to be exactly, by splitting us, it's going to be exactly the product I03 beta 1 ABTR times I03 beta 2 TSCTT, TSC of T, whatever we had over there. Okay, so that's it. Good. So similarly, we can actually calculate the following. Similarly, we can calculate A star B cross C. And then the idea of proving this associativity property is actually to show that we get the same results on both sides of the equation. So if we calculate that, it's going to be equal to the following. So it's going to be, again, summing over all beta, summing over T and U, summing over beta 1, beta 2, such that beta 1 plus beta 2 is equal to beta, okay, of sums over R and S, exactly same thing. So G of RS, I0, okay, now first I'm multiplying B and C. So B cross C. So I'm going to write I03 beta 1 B C TR times I03 beta 2 A TST of T G to the TU Q to the beta, and then times T of Q. Okay, so if I compare this thing with the other thing, so you see what has changed really. Look at, so let's see here. So there is, I can do something. So right here, I know that by a covariance axiom, I'm cleaning it up, nothing bad, like really. This is the same as -1 to the degree of A times degree of T of S. I want to shuffle them around. So I03 beta 2 TSA T of T. Okay, let me see. Am I doing this exactly? You see this, guys? This C appears there. I'm moving this over there, okay? And also we have, by the degree axiom, that degree of A plus degree of T of S plus degree of TT is going to be equal to 0 modulo 2. It's going to be even degree. I'm looking at here. Then it follows that I03 beta 2 ATS T of T is going to be -1 to the degree of A times degree of TS plus degree of TT times I03 beta 2 TSA TFT. Okay, because this sum is going to be even, it's 0 mod 2, modulo 2 in that quotient ring, basically degree of TS, instead of degree of TS, I can just put degree of TS plus, A times degree of TS, A times degree of T, right? Because of the congruence. Okay, so I can do that, and then result of calculation, and also, and furthermore, sum from 1 to n degree of alpha I. Okay, so this is 2 times 1 minus g times dimension of x minus this thing plus 2 times 3g minus 3 plus n. This implies that degree of A plus degree of B plus degree of C plus degree of T and T is equal to 0 mod 2. So basically, result of this thing, final thing, is that you will get the same answer. Shuffling these invariants around, and the fact that the sum of degrees are going to be even numbers shows you that this product that we calculated before, this right here, is going to be exactly equal to basically this product. Okay, therefore, A cross B cross C is going to be the same as A cross or star B star C. Okay, so the degrees are the same, and then shuffling them just flips the sign, and then that can be absorbed into the sum, so you will get the same identity. But I actually suggest you to kind of, if you really want to learn this and read this, write it in a nice clean piece of paper and re-investigate it again based on what I said. Any questions? Okay. All right. So let's see. Let me prove one more properties and then finish the class today. So here is another proposition. There's another proposition. If A and B are complexified cohomology classes, are homogeneous, also element, homogeneous. Okay, then A cross B, A star B, I keep saying cross, A star B is the sum over L of CL, where CL are homogeneous. Homogeneous classes, with the condition that, so such that degree of CL is going to be degree of A plus degree of B mod 2. Okay. Moreover, if I look at the kahler class, the class of the divisor defined by the canonical bundle of X, which is H upper 2 X with integral coefficient, then this is divisible by an integer. Let's call that integer something, say R, integer R, and then we can actually see that degree of CL is going to be degree of A congruent to degree of A plus degree of B mod 2 times this integer. Okay, so very kind of, I include this proof in here since G of ij is not going to be, is not equal to 0 only if, only if degree of Ti plus degree of Tj is 2 times dimension of X, right? Otherwise, if this is not equal to the case, because Gij is the intersection product, the only way that you can get non-vanishing is that you have some non-trivial intersection. If these things do not add up, because Gij is by definition Ti, car product with Tj over X, this is the complex dimension of X. If these do not add up to the dimension of X, which is 2 times complex dimension, then you will get all of the entries of that matrix will be equal to 0. So if that is the case, then because this is non-zero, only if this happens, then the degree condition implies that Tj has a non-zero coefficient only if degree of A plus degree of B is equal to degree of Tj minus 2 times intersection of omega is against beta. And that's basically the proof. Okay, so you look at, expand the product, look at the coefficient of Tj, and then you can actually see that if A and B are homogeneous elements, then this condition needs to be satisfied. So if that's the case, then that particularly means that the product of A and B has degree exactly this, which is degree of A plus degree of B modulo 2 times intersection product, and that's just R, basically. Canonical class against beta. All right, so these are, I think, good place to really stop, because we put a very horrendous calculation today, so I wanted to stare at it for a while. Okay, any questions? Properties, and maybe I discuss a little bit about, no, I think we have a while to go to the big quantum cohomology. Yeah.